This problem is going to start off the same way. We're starting off with right triangle, ABC. AC is the hypotenuse, B is the right angle. And through angle-angle similarity, we've seen that triangle ABC, the whole triangle, is similar to triangle ADB, the smaller right triangle, which is also similar to triangle BDC, this medium right triangle. And they're all similar through angle-angle similarity. So because they're all similar, the sides are all proportional, and we can look at the ratios of corresponding sides and see that they're all equal. And in this instance, I want to look at the ratio of the shorter of the two legs to the hypotenuse of the triangle in each of these three triangles. So we're going to look at the ratio of the shorter leg to the hypotenuse in each case. In the whole triangle, in triangle ABC, the shorter leg is AB, and the hypotenuse is AC. And then in the smaller triangle, the smallest of them, the short leg is AD, and the hypotenuse is AB. And in the medium triangle, in triangle BDC, the short leg is BD, and the hypotenuse is BC. So in the last one, we saw a place where we had a geometric means relationship. We had the same length in the means position of two of our proportions. In this one here, I notice we have AB shows up twice, but not in the means position, in our extremes position. But we know that we can take the reciprocal or exchange the means or reformat this proportion in a way that's useful to us. So I could take this and say, okay, well, either just flip these positions so that these are in the means, or take the reciprocal, that'll put them in the means positions, just to show that we have a geometric means relationship. Let's do it by, I'm just going to flip-flop these two. So AD over AB is equal to AB over AC. And so now we have the same value in the means positions. So let's look at where these things are and what our means, geometric mean relationship is. So AB, that's in the means position, so I can call that X. And then my extremes positions, I have AD and AC. So AD is this part of the whole hypotenuse that is adjacent to the leg. It's the piece of the hypotenuse closest to the leg that we're dealing with. I'm talking about the entire triangle here. So I can call this part here A. And then AC is the entire hypotenuse of the whole triangle, so that this whole distance here is B. And that way I can make this look like my traditional geometric mean setup, so that A to X is equal to X to B. So what does this say for us then in terms of the triangle here? Well, again, we've got the altitude drawn to the hypotenuse. That's what set up this case. It makes these three similar right triangles. And now the length of one of the legs of the triangle is the geometric mean of the piece of the hypotenuse adjacent to the leg, formed by that altitude, and the entire hypotenuse. So again, if I have any two of these three values, then I can find the third value. And this could also come, maybe if I got B and then I got this distance here, DC, then I could just use subtraction to find that, and I could find that length. And this, in combination with the other geometric mean relationship we have, means that I can really find many of the measures within these triangles just being given a limited amount of information. So now it's time to practice a bunch of these.